Okay, here we go. I hope everyone is either having a good spring break if you're starting this a little early, or you had a good spring break and you're back, and I'm off to the conference. So this week you're going to look at 5.4 and 5.5 on your own with my videos, and of course look in the book. The book does a great job explaining this, but I've used a combination of this video capture with my voiceover and the PowerPoints and Geogebra to try to walk you through some of this stuff like I would if I was there in class. So in 5.2, we talked about analytical geometry or analytic geometry, putting coordinates on points so that we can do things like distance and midpoints and angles and things like that. And then in 5.3, we talked about transformations, the rigid motions that send things to congruent copies. We called those isometries. We had translations, reflections, rotations, and then glide reflections, which were combinations of translations and reflections. And then the similarity transformations, homotheties, dilations, the simpler word for that, where we send things to similar copies instead of congruent copies. We change the size but keep the shape the same. In 5.4, we're going to see how to actually get formulas for that stuff, how to put coordinates on the transformations. And we're going to talk about that, which is called analytic transformations or analytical transformations. The first thing we have to do is talk just a little bit about vectors. In order to understand translations in particular, we need to know about vectors. Okay, so hopefully you've studied this in physics and or calculus 3 or somewhere in there you've looked at vectors in math. Vectors are pretty simple. They're just in two dimension. The vectors are arrows that have magnitude and direction. Okay, so the letters matter. PQ is different from QP. The direction matters on a vector. So PQ is pointing from P toward Q. So P would be called the initial point and Q would be called the terminal point. The magnitude is just the distance between PQ, if we think of that as a segment or the distance between the 2 points. The direction, if you were to draw a horizontal line or a line parallel to the x-axis and then measure counterclockwise the positive angle there, that would be the angle of inclination for PQ, and I'll show a picture of that here in a minute. To work with vectors, since they can be anywhere in the plane, it's usually a lot easier though to actually talk about their position vectors. So a position vector is a vector that has its initial point at the origin. And so any vector in the plane, actually all we have to do is subtract the x and y coordinates to find a position vector. It's very easy. So if r, and again the direction matters, SR would have the opposite signs. If we're going from R to S, if I subtract C minus A, I'll get the change in x to go from R to S. So my position vector's x coordinate would be C minus A. And then the same thing with the y's. Again, we're going from R to S, so do D minus B, I would get the change in y to go from R to S. So my position vector would just be C minus A, D minus B. Let's take a look at that in GeoGebra. Okay, hopefully I've got this set up correctly this time. I've made a couple of mistakes, but I think I've fixed them. I've got O as the origin and P is going to be our position vector. I've actually got it set up so that's the point I can move here. I can move A around, but A prime is determined by the position vector in this construction. But I'm thinking of this in terms of the definition as the vector A prime, which has the magnitude being whatever the distance is from A to A prime, and here's the direction, the angle of inclination. If I were to make this line horizontal, parallel to the x-axis, this horizontal line here, the angle between measured in the counterclockwise direction from that to here, it'd be from the positive x-axis if you're in standard position to the arrow. That's the angle of inclination, which is exactly the same because of the dimensions here as this angle. So the position vector, if we have the same change in x and the change in y, these two are going to be the hypotenuse of I'm getting tongue-tied here, the hypotenuse of congruent triangles. Okay, so this, if you look at these two, x plus h minus x would be h, y plus k minus y would be k. Okay, so that's how you find the position vector. Just do the change in x and the change in y, and you can find the position vector that'll have the same distance and the same angle, the same magnitude and direction, but it's always centered at the origin, which makes it easier to work with. Okay, and let's look at a couple of quick examples now of using the position vector to find the magnitude and direction. You could draw the actual vector and do this, but I think it's a little bit easier to always just convert to the position vector and then do it. Okay, so we're going to start with 3.2 and 4.4, which winds up in quadrant 1, which makes it a really simple example to start with. Okay, so here we go. So here's a picture of that. So I don't have the actual vector PQ, I have the position vector plotted. If we do 4 minus 3, the change in x is 1. 4 minus 2, the change in y is 2. So the position vector is 1, 2. And a lot of books will use the angled brackets for vectors. I've used the less than and greater than symbols to make them quickly here in Geogebra. So I take 1, 2 and actually plot that. Plot the point 1, 2 and then draw your line, which in terms of a vector would be the arrow from 0 to the point 1, 2. So the magnitude of that thing is just the Pythagorean theorem. It's always going to be, if the position vectors a and b, it's going to be the square root of a squared plus b squared, which turns out to be the square root of 5 for this one. The angle's a little bit trickier. It depends on the quadrant. The reference angle will always be the inverse or arctangent of b over a. If you make the triangle, opposite over adjacent, it's going to be b over a. Again, if b is the y-coordinate and a is the x-coordinate for the position vector. If I do the arctangent here, I get 60 in degrees, 63.43. That is actually the angle for this vector because this is in quadrant 1. Okay? Let me show you one example where it's in a different quadrant. So this one's very similar. I've just tweaked it a little bit. This time the position vector turns out to be 1, negative 2. I've swapped it so that 2 minus 4 gives me a negative 2. When I plot that, it's in quadrant 4. Okay? Now the magnitude, let me draw the vector as well. So it's actually this arrow going between those points. The magnitude, though, is the length of the hypotenuse of that triangle, which is still square root of 5 because I still have 1 and 2 for the sides of this triangle. And the tangent of theta is still b over a is going to be, it's actually negative here. The absolute value is all I really care about at this case. If you want to slap that on it, you either get 2 or negative 2. The arctangent of that, and tangent's an odd function, you'll either get positive or negative 63.43. This actual angle measured in standard position would be negative 63.43 degrees in the triangle. But the angle, you can see here, theta is the angle I need for my vector. This depends on which quadrant you're in. If you're in quadrant 2, it'd be 180 degrees or pi minus your angle. If you're in quadrant 3, it's going to be 180 degrees plus your angle. In quadrant 4, the angle that I want is 360, the complete circle, minus the 63.43 degrees, which gives me 296.57. Let's see if that what it says if I turn this on. Yep, exactly. 296.57 degrees is that angle. Okay. So that's how, if you know the position vector, you can find the magnitude and the direction. The magnitude's always the square root of a squared plus b squared. The tangent of theta will be b over a, or you can even slap absolute value on that if you want to, if you just think about the angle in the triangle. But then you have to look at that in its positioning and either add or subtract from 180, or in this case subtract from 360 to find the actual angle measured counterclockwise from the positive x-axis.